Hakan selamlar, hoş geldin. Şöyle koyalım. Şöyle aldık. Şuraları kapatalım. Hop, hop, hop.
Now, the example that I would like to work with and that I'm particularly fond of is that of OpenAI's GPT-2. So GPT to work with, sense of what this actually looks like when these models.
Evet, bugün daha da geç kaldım. O yüzden hemen başlayacağım. Selam Yakup, hoş geldin. Şimdi ilk iki bölümü bu Andrei Karpathy'nin ilk iki bölümünü izlemiştik. Ya bölüm dediğim aslında 3,5 saatlik bir video. Dur bir saniye. Bu da ne? 31.8. Yanlış. Bu kadar az izlemiş olamayız.
Models are trained. Now, the example that I would like to work with and that I'm particularly fond of
2
is
saati
that of OpenAI's
doldurmuşuz.
GPT-2. So GPT, first one. So we start with and they don't see characters like our eyes do. And so very simple character level tasks often fail. So for example, eyes do. And about tokens, models use the edges of the technology to be kind of aware of over time. So as an example, the models are not very good with all kinds of spelling related tasks. They're not very good at it.
Tamam, burada bir yerde kalmıştık. 3 saatlik video. Neden buraya geldi anlamadım. Ama 2 saatini bitirmiştik. Pre-training, post-training. Halüsinasyonlardan bahsetmişti. Ondan sonra herhangi bir task'ı yaptırırken tokenlara dağıtma olayı vardı. Gibi gibi. Şimdi bakalım nereden devam
At it.
edecek.
And I told you that we would loop
İkinci
back around
saatte,
to
üçüncü saat
tokenization.
arasında izleyelim.
And the reason to do for this is that the models, they don't see the characters, they see tokens. And their entire world is about tokens, which are
Ses
these little
geliyor değil mi?
text chunks. And so they don't see characters like our eyes do. And so very simple character level tasks often fail. So for example, I'm giving it a string, ubiquitous, and I'm asking it to print only every third character starting with the first one. So we start with U, and then we should go every third. So 1, 2, 3, Q should be next, and then etc. So this I see is not correct. And again, my hypothesis is that this is, again, the mental arithmetic here is failing, number one, a little bit. But number two, I think the more important issue here is that if you go to tick tokenizer and you look at ubiquitous, we see that it is 3 tokens, right? So you and I see ubiquitous, and we can easily access the individual letters because we kind of see them. And when we have it in the working memory of our visual sort of field, we can really easily index into every third letter, and I can do that task. But the models don't have access to the individual letters. They see this as these 3 tokens. And remember, these models are trained from scratch on the internet, and all these basically the model has to discover how many of all these different letters are packed into all these different tokens. And the reason we even use tokens is mostly for efficiency. But I think a lot of people are interested to delete tokens entirely. Like, we should really have character level or byte level models. It's just that would create very long sequences, and people don't know how to deal with that right now. So while we have the token world, any kind of spelling tasks are not actually expected to work super well. So because I know that spelling is not a strong suit because of tokenization, I can again ask it to lean on tools. So I can just say use code, and I would again expect this to work because the task of copy pasting ubiquitous into the Python interpreter is much easier, and then we're leaning on Python interpreter to manipulate the characters of this string. So when I say use code, ubiquitous, yes, it indexes into every third character, and the actual truth is UQTS, which looks correct to me. So again, an example of spelling related tasks not working very well. A very famous example of that recently is how many R are there in strawberry? And this went viral many times. And basically the models now get it correct. They say there are 3 R's in strawberry, but for a very long time, all the state-of-the-art models would insist that there are only 2 R's in strawberry. And this caused a lot of, ruckus because, is that a word? I think so. Because it's just kind of like, why are the models so brilliant and they can solve math Olympiad questions, but they can't like count R's in strawberry? And the answer for that, again, is I've kind of built up to it kind of slowly. But number one, the models don't see characters, they see tokens. And number two, they are not very good at counting. And so here we are combining the difficulty of seeing the characters with the difficulty of counting. And that's why the models struggled with this, even though I think by now, honestly, I think OpenAI may have hard-coded the answer here, or I'm not sure what they did. But this specific query now works. So models are not very good at spelling, and there's a bunch of other little sharp edges, and I don't want to go into all of them. I just want to show you a few examples of things to be aware of, and when you're using these models in practice. I don't actually want to have a comprehensive analysis here of all the ways that the models are kind of like falling short. I just want to make the point that there are some jagged edges here and there, and we've discussed a few of them, and a few of them make sense, but some of them also will just not make as much sense, and they're kind of like you're left scratching your head even if you understand in depth how these models work. And a good example of that recently is the following. The models are not very good at very simple questions like this. And this is shocking to a lot of people because these problems can solve complex math problems. They can answer PhD grade physics, chemistry, biology questions much better than I can, but sometimes they fall short in like super simple problems like this. So here we go. 9.11 is bigger than 9.9, and it justifies this in some way, but obviously, and then at the end, okay, it flips its decision later. So I don't believe that this is very reproducible. Sometimes it flips around its answer. Sometimes it gets it right, sometimes it gets it wrong. Let's try again. Okay. Even though it might look larger, okay, so here it doesn't even correct itself in the end. If you ask many times, sometimes it gets it right too. But how is it that the model can do so great at Olympiad grade problems, but then fail on very simple problems like this? And I think this one is, as I mentioned, a little bit of a head scratcher. It turns out that a bunch of people studied this in depth, and I haven't actually read the paper, but what I was told by this team was that when you scrutinize the activations inside the neural network, when you look at some of the features and what features turn on or off and what neurons turn on or off, a bunch of neurons inside the neural network light up that are usually associated with Bible verses. And so I think the model is kind of like reminded that these almost look like Bible verse markers. And in a Bible verse setting, 9.11 would come after 9.9. And so basically the model somehow finds it like cognitively very distracting that in Bible verses 9.11 would be greater. Even though here it's actually trying to justify it and come up to the answer with a math, it still ends up with the wrong answer here. So it basically just doesn't fully make sense, and it's not fully understood, and there's a few jagged issues like that. So that's why treat this as what it is, which is a stochastic system that is really magical, but that you can't also fully trust. And you want to use it as a tool, not as something that you kind of like let it rip on a problem and copy paste the results. Okay, so we have now covered two major stages of training of large language models. We saw that in the first stage, this is called the pre-training stage, we are basically training on internet documents. And when you train a language model on internet documents, you get what's called a base model, and it's basically an internet document simulator, right? Now we saw that this is an interesting artifact, and this takes many months to train on thousands of computers, and it's kind of a lossy compression of the internet. And it's extremely interesting, but it's not directly useful because we don't want to sample internet documents. We want to ask questions of an AI and have it respond to our questions. So for that, we need an assistant. And we saw that we can actually construct an assistant in the process of post-training, and specifically in the process of supervised fine-tuning, as we call it. So in this stage, we saw that it's algorithmically identical to pre-training. Nothing is going to change. The only thing that changes is the dataset. So instead of internet documents, we now want to create and curate a very nice dataset of conversations. So we want millions of conversations on all kinds of diverse topics between a human and an assistant. And fundamentally, these conversations are created by humans. So humans write the prompts and humans write the ideal responses. And they do that based on labeling documentations. Now, in the modern stack, it's not actually done fully and manually by humans, right? They actually now have a lot of help from these tools, so we can use language models. to help us create these data sets, and that's done extensively. But fundamentally, it's all still coming from human curation at the end. So we create these conversations, that now becomes our data set, we fine tune on it or continue training on it, and we get an assistant. And then we kind of shifted gears and started talking about some of the kind of cognitive implications of what this assistant is like. And we saw that, for example, the assistant will hallucinate if you don't take some sort of mitigations towards it. So we saw that hallucinations would be common, and then we looked at some of the mitigations of those hallucinations. And then we saw that the models are quite impressive and can do a lot of stuff in their head, but we saw that they can also lean on tools to become better. So for example, we can lean on a web search in order to hallucinate less, and to maybe bring up some more recent information or something like that. Or we can lean on tools like code interpreter, so the LLM can write some code and actually run it and see the results. So these are some of the topics we looked at so far. Now what I'd like to do is I'd like to cover the last and major stage.
Şimdi last şeye geçmeden önce 10 dakikalık yorum yapalım. Biraz önceki bölümden örnek vermeye devam etti aslında. Şimdi bazı şeyleri sorduğu zaman o halüsinasyondan yine devreye giriyor. 9.11 ile 9.9'un hangisinin daha büyük olduğunu söyledi ama iki denemede bile 9.11'in daha büyük olduğunu söyledi. Ya da ubiquitous diye bir kelime vardı. Her üç kelimeden her üçüncü karakterlerden her üçüncüsünü yazdırır mısın diye onu da yanlış yazdırdı. Ama ne zaman ki şey dese bana bunu kodla yapar mısın diye o zaman doğru yapacaktı. Çünkü ilk durumda işlem yaparken TikTokenizer'ı kullanıyor ya mesela. TikTokenizer'da gösterdi. Ubiquitous'e baktığın zaman tuhaf şekilde tokenlara ayrılmış. Yani 3 tane token'a erişim var. Large Language Model'ın 3 tane token görüyor Ubiquitous'a baktığı zaman. Ama e, üçer sonraki karakterleri ver dediği zaman orada saçmalıyor. Yanlış bir cevap vermiş. Ne zaman ki bunu bana kodla yap diyor, o zaman alıyor, Python'a veriyor. Python'la onu doğru yapabiliyor. Çünkü Python tarafından yani programlama dilleri bunları zaten iyi yapabiliyor. Sadece nasıl yapması gerektiğini söylüyor koda. Aynı şekilde şeyi de hangisi diğerinden daha büyük dediğinde de onu da yine kodla yap dediğinde gayet doğru yapıyor. Diğer türlü hallucination. Bunun halüsinasyonları çözebilmek için işte bu post training'de yaptıkları conversation'lar var ya onların bayağı önemi var. İşte şu human labeler dediği var ya ciddi ciddi bazı insanlar var. Bu conversation'ları hazırlıyorlar bunların üzerine uzman. Ama tabii internetten aldığın doküman kadar fazla olmuyor. O 340 terabaytlık datadan bahsetmiştik FileMap. Ama burada insanlar işte 10.000 tane belki 100.000 tane bir conversation falan ayarlıyorlar. Dolayısıyla insanlar arasında geçen o insanımsı conversation'lar var olan pre-training'de eğitilmiş olan dataların daha iyi cevap verebilmesini sağlıyor LLM tarafından. Şimdiye kadar bunları anlattı. Bakalım bir sonraki şeyde neyi anlatacak?
Of this pipeline, and that is reinforcement learning. So reinforcement learning is still kind of thought.
O reinforcement learning benim üniversitedeki bitirme tezimdi. Bir 17 sene oldu bunu yapalı. Reinforcement learning'e tez yazmıştım bununla alakalı. Tez yazdığım konu da karıncalardı. Karıncaların yaşam tarzı, kolonileri nasıl buluyorlar, nasıl hareket ediyorlar falan. O reinforcement learning'e çok güzel bir örnekti. C'de yazmıştım onu. Bakalım buradan nereden örnek gösterecek.
Thought to be under the umbrella of post-training, but it is the last third major stage, and it's a different way of training language models, and usually follows as this third step. So inside companies like OpenAI, you will start here, and these are all separate teams. So there's a team doing data for pre-training, and a team doing training for pre-training, and then there's a team doing all the conversation generation in a different team that is kind of doing the supervised fine-tuning, and then there will be a team for the reinforcement learning as well. So it's kind of like a handoff of these models. You get your base model, then you fine-tune it to be an assistant, and then you go into reinforcement learning, which we'll talk about now. So that's kind of like the major flow. And so let's now focus on reinforcement learning, the last major stage of training. And let me first actually motivate it and why we would want to do reinforcement learning and what it looks like on a high level. So I would now like to try to motivate the reinforcement learning stage and what it corresponds to with something that you're probably familiar with. And that is basically going to school. So just like you went to school to become really good at something, we want to take large language models through school. And really what we're doing is we have a few paradigms of ways of giving them knowledge or transferring skills. So in particular, when we're working with textbooks in school, you'll see that there are three major kind of pieces of information in these textbooks, three classes of information. The first thing you'll see is that you'll see a lot of exposition. And by the way, this is a totally random book I pulled from the internet. I think it's some kind of an organic chemistry or something, I'm not sure. But the important thing is that you'll see that most of the text, most of it is kind of just like the meat of it, is exposition. It's kind of like background knowledge, etc. As you are reading through the words of this exposition, you can think of that roughly as training on that data. So, and that's why when you're reading through this stuff, this background knowledge and all this context information, it's kind of equivalent to pre-training. So it's where we build sort of like a knowledge base of this data and get a sense of the topic. The next major kind of information that you will see is these problems and with their worked solutions. So basically, a human expert, in this case, the author of this book, has given us not just a problem, but has also worked through the solution. And the solution is basically like equivalent to having like this ideal response for an assistant. So it's basically the expert is showing us how to solve the problem in its kind of like in its full form. So as we are reading the solution, we are basically training on the expert data. And then later we can try to imitate the expert. And basically, that roughly corresponds to having the SFT model. That's what it would be doing. So basically, we've already done pre-training, and we've already covered this imitation of experts and how they solve these problems. And the third stage of reinforcement learning is basically the practice problems. So sometimes you'll see this is just a single practice problem here, but of course there will be usually many practice problems at the end of each chapter in any textbook. And practice problems, of course, we know are critical for learning, because what are they getting you to do? They're getting you to practice yourself and discover ways of solving these problems yourself. And so what you get in a practice problem is you get a problem description, but you're not given the solution, but you are given the final answer, usually in the answer key of the textbook. And so you know the final answer that you're trying to get to, and you have the problem statement, but you don't have the solution. You are trying to practice the solution. You're trying out many different things, and you're seeing what gets you to the final solution the best. And so you're discovering how to solve these problems. So, and in the process of that, you're relying on, number one, the background information, which comes from pre-training, and number two, maybe a little bit of imitation of human experts. And you can probably try similar kinds of solutions and so on. So we've done this, and now in this section, we're going to try to practice. And so we're going to be given prompts, we're going to be given solutions, the final answers, but we're not going to be given expert solutions. We have to practice and try stuff out. And that's what reinforcement learning is about. Okay, so let's go back to the problem that we worked with previously, just so we have a concrete example to talk through as we explore sort of the topic here. So I'm here in the tick tokenizer because I'd also like to, well, I get a text box, which is useful. But number two, I want to remind you again that we're always working with one-dimensional token sequences. And so I actually prefer this view because this is like the native view of the LLM, if that makes sense. Like this is what it actually sees. It sees token IDs, right? Okay. So Emily buys 3 apples and 2 oranges. Each orange is $2. The total cost of all the fruit is $13. What is the cost of each apple? And what I'd like you to appreciate here is these are like 4 possible candidate solutions as an example. And they all reach the answer 3. Now, what I'd like you to appreciate at this point is that if I'm the human data labeler that is creating a conversation to be entered into the training set, I don't actually really know which of these conversations to add to the data set. Some of these conversations kind of set up a system of equations. Some of them sort of like just talk through it in English. And some of them just kind of like skip right through to the solution. If you look at ChatGPT, for example, and you give it this question, it defines a system of variables and it kind of like does this little thing. What we have to appreciate and differentiate between though is Um, the first purpose of a solution is to reach the right answer. Of course, we want to get the final answer 3. That is the important purpose here. But there's a kind of like a secondary purpose as well, where here we are also just kind of trying to make it like nice for the human, because we're kind of assuming that the person wants to see the solution, they want to see the intermediate steps, we want to present it nicely, etc. So there are two separate things going on here. Number one is the presentation for the human, but number two, we're trying to actually get the right answer. So let's, for the moment, focus on just reaching the final answer. If we only care about the final answer, then which of these is the optimal or like the best prompt, the best solution for the LLM to reach the right answer? And what I'm trying to get at is we don't know. Me, as a human labeler, I would not know which one of these is best. So as an example, we saw earlier on when we looked at the token sequences here and the mental arithmetic and reasoning, we saw that for each token, we can only spend basically a finite amount of compute here that is not very large, or you should think about it that way. And so we can't actually make too big of a leap in any one token, is maybe the way to think about it. So as an example, in this one, what's really nice about it is that it's very few tokens, so it's going to take us a very short amount of time to get to the answer. But right here, when we're doing 13 minus 4 divide 3 equals, right in this token here, we're actually asking for a lot of computation to happen on that single individual token. And so maybe this is a bad example to give to the LLM because it's kind of incentivizing it to skip through the calculations very quickly, and it's going to actually make mistakes in its mental arithmetic. So maybe it would work better to like spread it out more. Maybe it would be better to set it up as an equation. Maybe it would be better to talk through it. We fundamentally don't know, and we don't know because what is easy for you or I, as human labelers, what's easy for us or hard for us is different than what's easy or hard for the LLM. Its cognition is different, and the token sequences are kind of like different hard for it. And so some of the token sequences here that are trivial for me might be very too much of a leap for the LLM. So right here, this token would be way too hard. But conversely, many of the tokens that I'm creating here might be just trivial to the LLM, and we're just wasting tokens. Like, why waste all these tokens when this is all trivial? So if the only thing we care about is reaching the final answer, and we're separating out the issue of the presentation to the human, then we don't actually really know how to annotate this example. We don't know what solution to give to the LLM because we are not the LLM. And it's clear here in the case of like the math example, but this is actually like a very pervasive issue. Like for our knowledge is not LLM's knowledge. Like the LLM actually has a ton of knowledge of PhD in math and physics and chemistry and whatnot. So in many ways, it actually knows more than I do. And I'm potentially not utilizing that knowledge in its problem solving. But conversely, I might be injecting a bunch of knowledge in my solutions that the LLM doesn't know in its parameters. And then those are like sudden leaps that are very confusing to the model. And so our cognitions are different, and I don't really know what to put here if all we care about is reaching the final solution and doing it economically, ideally. And so, long story short, we are not in a good position to create these token sequences for the LLM. And they're useful by imitation to initialize the system, but we really want the LLM to discover the token sequences that work for it. It needs to find for itself what token sequence reliably gets to the answer given the prompt. And it needs to discover that in a process of reinforcement learning and of trial and error. So let's see how this example would work like in reinforcement learning. Okay, so we're now back in the Hugging Face inference playground. And that just allows me to very easily call different kinds of models. So as an example here on the top right, I chose the Gemma 2 billion parameter model. So 2 billion is very, very small. So this is a tiny model, but it's okay. So we're going to give it, the way that reinforcement learning will basically work is actually quite simple. We need to try many different kinds of solutions, and we want to see which solutions work well or not. So we're basically going to take the prompt, we're going to run the model, and the model generates a solution. And then we're going to inspect the solution. And we know that the correct answer for this one is $3. And so indeed the model gets it correct. It says it's $3, so this is correct. So that's just one attempt at the solution. So now we're going to delete this and we're going to rerun it again. Let's try a second attempt. So the model solves it in a bit slightly different way, right? Every single attempt will be a different generation because these models are stochastic systems. Remember that at every single token here, we have a probability distribution and we're sampling from that distribution. So we end up kind of going down slightly different paths. And so this is a second solution that also ends in the correct answer. Now we're going to delete that. Let's go a third time. Okay, so again, slightly different solution, but also gets it correct. Now we can actually repeat this many times. And so in practice, you might actually sample thousands of independent solutions or even like a million solutions for just a single prompt. And some of them will be correct and some of them will not be very correct. And basically what we want to do is we want to encourage the solutions that lead to correct answers. So let's take a look at what that looks like. So if we come back over here, here's kind of like a cartoon diagram of what this is looking like. We have a prompt, and then we tried many different solutions in parallel. And some of the solutions might go well, so they get the right answer, which is in green. And some of the solutions might go poorly and may not reach the right answer, which is red. Now, this problem here, unfortunately, is not the best example because it's a trivial prompt. And as we saw, even like a 2 billion parameter model always gets it right. So it's not the best example in that sense. But let's just exercise some imagination here and let's just suppose that the green ones are good and the red ones are bad. Okay, so we generated 15 solutions, only 4 of them got the right answer. And so now what we want to do is basically we want to encourage the kinds of solutions that lead to right answers. So whatever token sequences happened in these red solutions, obviously something went wrong along the way somewhere. And this was not a good path to take through the solution. And whatever token sequences there were in these green solutions, well, things went pretty well in this situation. And so we want to do more things like it in prompts like this. And the way we encourage this kind of a behavior in the future is we basically train on these sequences. But these training sequences now are not coming from expert human annotators. There's no human who decided that this is the correct solution. This solution came from the model itself. So the model is practicing here. It's tried out a few solutions. 4 of them seem to have worked. And now the model will kind of like train on them. And this corresponds to a student basically looking at their solutions and being like, okay, well, this one worked really well. So this is how I should be solving these kinds of problems. And here in this example, there are many different ways to actually like really tweak the methodology a little bit here. But just to give the core idea across, maybe it's simplest to just think about taking the single best solution out of these 4, like say this one. That's why it was yellow. So this is the solution that not only led to the right answer, but maybe had some other nice properties. Maybe it was the shortest one, or it looked nicest in some ways, or there's other criteria you could think of as an example. But we're gonna decide that this is the top solution. We're gonna train on it, and then the model will be slightly more likely, once you do the parameter update, to take this path in this kind of a setting in the future. But you have to remember that we're gonna run many different diverse prompts across lots of math problems and physics problems and whatever there might be. So tens of thousands of prompts maybe have in mind. There's thousands of solutions per prompt. And so this is all happening kind of like at the same time. And as we're iterating this process, the model is discovering for itself what kinds of token sequences lead it to correct answers. It's not coming from a human annotator. The model is kind of like playing in this playground, and it knows what it's trying to get to, and is discovering sequences that work for it. These are sequences that don't make any mental leaps. They seem to work reliably and statistically, and fully utilize the knowledge of the model as it has it. And so this is the process of reinforcement learning. It's basically a guess and check. We're going to guess many different types of solutions. We're going to check them, and we're going to do more of what worked in the future. And that is reinforcement learning. So in the context of what came before, we see now that the SFT model, the supervised fine-tuning model, it's still helpful because it still kind of like initializes the model a little bit into the vicinity of the correct solutions. So it's kind of like a initialization of the model in the sense that it kind of gets the model to, take solutions, like write out solutions, and maybe it has an understanding of setting up a system of equations, or maybe it kind of like talks through a solution. So it gets you into the vicinity of correct solutions. But reinforcement learning is where everything gets dialed in. We really discover the solutions that work for the model, get the right answers, we encourage them, and then the model just kind of like gets better over time. Okay, so that is the high level process for how we train large language models. In
Kısa bir update geçelim yine. Bu sefer 10 dakikayı da geçti. 16 dakika oldu. Şimdi burada reinforcement learning'den bahsediyor. Bu SFT dediği Supervised Fine Tuning Model diye geçiyor. Reinforcement, şimdi öncekinde neydi? Bir şey soruyordun, cevap veriyordu, değil mi? Post training'de görmüştük bunu. Pre training'de de şey vardı. Bir şey yazıyorsun, inference yani sonrasını tamamlamaya çalışıyor. Ama request response bu kadar. Ama burada öyle bir şey var ki reinforcement learning tarafında sen bir şey sorduğun zaman bir cevap geliyor. Hatta ben bunu şeye benzetiyorum. ChatGPT'de iki tane versiyonu var bildiğim kadarıyla bunun. Bir tanesi sana soru sorduğunda iki tane paralelde cevap veriyor. Belki karşılaşmışsınızdır siz de. Hangisini istiyorsun diye. Hangisi sana uyuyor. Bir tanesini seçiyorsun. Oradan bence şey yapıyor. Bir sonraki buna gelecek olan cevaplara ona göre bir path çizecek. Çünkü burada sana verdiği cevapların hepsi aslında tokenlar üzerinde yaptığı olasılıksal hesaplamalar ve sen her sorduğunda ayrı bir path'ten gitmeye çalışıyor. Çünkü olasılıkta şey düşünün. Yani yazı tura atıyorsun. Her zaman aynı gelmeyebilir. Belki boyutu daha fazladır. Olasılık olarak yazı tura iki seçenekte de belki daha fazla seçenek var tabii ki de. Ama şey gibi düşünün. Cevaba giderken dallanıyor, seyahat ediyor. Bir noktaya geldi. Şuradan mı gideyim, buradan mı gideyim? Bir olasılık daha gidiyor. İleride bir daha ayrım çıkıyor. Bir olasılık daha gibi. Burada ama verdiğin cevaba göre bir tanesi ikili soruyor sana paralelde. İkili cevap veriyor. Sen birini seçiyorsun. Diğeri de cevap veriyor ya sana. Cevabın her cevabın altında like butonu var, dislike butonu var. Muhtemelen orada like, dislike demene göre bu arkadaş bir sonraki cevabını verirken istatistiksel hesaplama yapıyor ya, parametrelerini ona göre ayarlıyor. Yaptığı şey bu reinforcement learning'de. Ben şeyden bahsetmiştim. Üniversite bitirme tezimde vardı. Karıncaların yolunu bulma olayında. Orada da bu reinforcement learning olayı vardı. İşte muhtemelen hatırladığım kadarıyla hani gittikleri o hava baloncukları falan var ya, seyahat ederken böyle odaları var. Hava odaları diye geçiyor. Yerini nasıl bulabiliyor, nereye gideceğini. Bazı yerlerde yanlış gittiğinde bir daha oraya uğramıyor falan. Bunlar da reinforcement, yani karıncanın seyahat etmesini reinforcement learning ile yapmaya çalışıyorlardı. Yani bir robot olduğunu düşün. Küçük bir robot oraya nasıl gidecek? Reinforcement learning ile yapıyordu. Şimdi bunu high level anlattı böyle. Ha, bu arada bu kitap örneğinde de şey vardı. Yani bir soru var. Bir de onun çözümü var. Çözümünü öğretiyorsun sen. Yani sana 3 tane çözüm verdi şeyde. Onlardan herhangi birini deniyor. Senin verdiğin okey ya da cancel'a göre kendini biraz daha iyileştiriyor. Şimdi daha detayına inecek galiba. Bir ona bakalım.
in short, we train them kind of very similar to how we train children. And basically, the only difference is that children go through chapters of books and they do all these different types of training exercises kind of within a chapter of each book. But instead, when we train AIs, it's almost like we kind of do it stage by stage, depending on the type of that stage. So, first, what we do is we do pre training, which, as we saw, is equivalent to basically reading all the expository material. So, we look at all the textbooks at the same time and we read all the exposition and we try to build a knowledge base. The second thing then is we go into the SFT stage, which is really looking at all the fixed sort of like solutions from human experts of all the different kinds of worked solutions across all the textbooks. And we just kind of get an SFT model which is able to imitate the experts, but does so kind of blindly. It just kind of like does its best guess, kind of just like trying to mimic statistically the expert behavior. And so that's what you get when you look at all the worked solutions. And then finally, in the last stage, we do all the practice problems in the RL stage. Across all the textbooks, we only do the practice problems. And that's how we get the RL model. So on a high level, the way we train LLMs is very much equivalent to the process that we use for training of children. The next point I would like to make is that actually these first two stages, pre-training and supervised fine-tuning, they've been around for years and they are very standard and everyone does them, all the different LLM providers. It is this last stage, the RL training, that is a lot more
Yani
early in its process.
aslında çok güzel bir örnek. Çocuklara verdiği bu reinforcement learning'in çocuk örneği bence güzeldi, yerinde oldu. Çünkü şey gibi düşünün. Evet, çocuklarda belki hissel olarak bazı bildikleri şeyler var ama çoğunluğunu yaşadıkça hani çok kısa zamanda öğreniyorlar ya. Bazılarını belki kendi gidiyor sobaya dokunduğunda bir daha dokunmuyor. Öğrenmiş oluyor onu. Yani bir sonraki hesaplamada sobayı hiç hesaba katmıyor bile. Artık onu elemiş oluyor. Bazen de ya o soruyor, sen cevap veriyor, öyle modelini geliştiriyor ya da sen söylüyorsun şöyle yap, böyle yap, böyle yapman gerekiyor diye. Orada da yine modelini genişletmiş oluyor aslında. Bence güzel
Possible
örnek.
and is not standard yet in the field. And so um, this stage is a lot more kind of early and nascent. And the reason for that is because I actually skipped over a ton of little details here in this process. The high level idea is very simple, it's trial and error learning. But there's a ton of details and little mathematical kind of like nuances to exactly how you pick the solutions that are the best and how much you train on them and what is the prompt distribution and how to set up the training run such that this actually works. So there's a lot of little details and knobs to the core idea that is very, very simple. And so getting the details right here is not trivial. And so a lot of companies, like for example OpenAI and other LLM providers, have experimented internally with reinforcement learning fine-tuning for LLMs for a while, but they've not talked about it publicly. It's all kind of done inside the company. And so that's why the paper from DeepSeek that came out very, very recently was such a big deal. Because this is a paper from this company called DeepSeek AI in China. And this paper really talked very publicly about reinforcement learning fine-tuning for large language models and how incredibly important it is for large language models and how it brings out a lot of reasoning capabilities in the models. We'll go into this in a second. So this paper reinvigorated the public interest of using RL for LLMs and gave a lot of the sort of nitty-gritty details that are needed to reproduce the results and actually get the stage to work for large language models. So let me take you briefly through this DeepSeek R1 paper and what happens when you actually correctly apply RL to language models and what that looks like and what that gives you. So the first thing I'll scroll to is this kind of figure 2 here, where we are looking at the improvement in how the models are solving mathematical problems. So this is the accuracy of solving mathematical problems on the AMI accuracy. And then we can go to the web page and we can see the kinds of problems that are actually in these the kinds of math problems that are being measured here. So these are simple math problems. You can pause the video if you like, but these are the kinds of problems that basically the models are being asked to solve. And you can see that in the beginning they're not doing very well, but then as you update the model with this many thousands of steps, their accuracy kind of continues to climb. So the models are improving and they're solving these problems with a higher accuracy as you do this trial and error on a large data set of these kinds of problems. And the models are discovering how to solve math problems. But even more incredible than the quantitative kind of results of solving these problems with a higher accuracy is the qualitative means by which the model achieves these results. So when we scroll down, one of the figures here that is kind of interesting is that later on in the optimization, the model seems to be using average length per response goes up. So the model seems to be using more tokens to get its higher accuracy results. So it's learning to create very, very long solutions. Why are these solutions very long? We can look at them qualitatively here. So basically what they discover is that the model's solutions get very, very long, partially because, so here's a question, and here's kind of the answer from the model. What the model learns to do, and this is an emergent property of the optimization, it just discovers that this is good for problem solving, is it starts to do stuff like this. Wait, that's an aha moment I can flag here. Let's reevaluate this step by step to identify if the correct sum can be. So what is the model doing here, right? The model is basically reevaluating steps. It has learned that it works better for accuracy to try out lots of ideas, try something from different perspectives, retrace, reframe, backtrack. It's doing a lot of the things that you and I are doing in the process of problem solving for mathematical questions, but it's rediscovering what happens in your head, not what you put down on the solution. And there is no human who can hard code this stuff in the ideal assistant response. This is only something that can be discovered in the process of reinforcement learning because you wouldn't know what to put here. This just turns out to work for the model and it improves its accuracy in problem solving. So the model learns what we call these chains of thought in your head, and it's an emergent property of the optimization. And that's what's bloating up the response lengths, but that's also what's increasing the accuracy of the problem solving. So what's incredible here is basically the model is discovering ways to think. It's learning what I like to call cognitive strategies of how you manipulate a problem and how you approach it from different perspectives how you pull in some analogies or do different kinds of things like that, and how you kind of try out many different things over time, check a result from different perspectives, and how you kind of solve problems. But here it's kind of discovered by the RL. So extremely incredible to see this emerge in the optimization without having to hard code it anywhere. The only thing we've given it are the correct answers, and this comes out from trying to just solve them correctly, which is incredible. Now let's go back to actually the problem that we've been working with, and let's take a look at what it would look like for this kind of a model, what we call reasoning or thinking model, to solve that problem. Okay, so recall that this is the problem we've been working with. And when I pasted it into ChatGPT 4.0, I'm getting this kind of a response. Let's take a look at what happens when you give this same query to what's called a reasoning or a thinking model. This is a model that was trained with reinforcement learning. So this model described in this paper, DeepSeek R1, is available on chat.deepseek.com. So this is kind of like the company that developed it is hosting it. You have to make sure that the Deep Think button is turned on to get the R1 model, as it's called. We can paste it here and run it. And so let's take a look at what happens now and what is the output of the model. Okay, so here's what it says. So this is previously what we get using basically what's an SFT approach, a supervised fine-tuning approach. This is like mimicking an expert solution. This is what we get from the RL model. Okay, let me try to figure this out. So Emily buys 3 apples and 2 oranges. Each orange costs $2. Total is 13. I need to find out blah, blah, blah. So here, as you're reading this, you can't escape thinking that this model is thinking. It's definitely pursuing the solution. It derives that it must cost $3, and then it says, wait a second, let me check my math again to be sure. And then it tries it from a slightly different perspective. And then it says, yep, all that checks out. I think that's the answer. I don't see any mistakes. Let me see if there's another way to approach the problem, maybe setting up an equation. Let's let the cost of one apple be $8, then blah, blah, blah. Yep, same answer. So definitely each apple is $3. All right, confident that that's correct. And then what it does once it sort of did the thinking process is it writes up the nice solution for the human. And so this is now considering, so this is more about the correctness aspect, and this is more about the presentation aspect, where it kind of like writes it out nicely and boxes in the correct answer at the bottom. And so what's incredible about this is we get this like thinking process of the model. And this is what's coming from the reinforcement learning process. This is what's bloating up the length of the token sequences. They're doing thinking and they're trying different ways. This is what's giving you higher accuracy in problem solving. And this is where we are seeing these aha moments and these different strategies and these ideas for how you can make sure that you're getting the correct answer. The last point I wanted to make is some people are a little bit nervous about putting, very sensitive data into chat.deepseek.com because this is a Chinese company, so people are a little bit careful and cagey with that a little bit. DeepSeek R1 is a model that was released by this company. So this is an open source model or open weights model. It is available for anyone to download and use. You will not be able to run it in its full, the full model in full precision. You won't run that on a MacBook, but or like a local device, because this is a fairly large model. But many companies are hosting the full largest model. One of those companies that I like to use is called Together.ai. So when you go to Together.ai, you sign up and you go to Playgrounds. You can select here in the chat DeepSeek R1, and there's many different kinds of other models that you can select here. These are all state-of-the-art models. So this is kind of similar to the Hugging Face inference playground that we've been playing with so far. But Together.ai will usually host all the state-of-the-art models. So select DeepSeek R1. You can try to ignore a lot of these. I think the default settings will often be okay. And we can put in this. And because the model was released by DeepSeek, what you're getting here should be basically equivalent to what you're getting here. Now, because of the randomness in the sampling, we're going to get something slightly different. But in principle, this should be identical in terms of the power of the model. And you should be able to see the same things quantitatively and qualitatively. But this model is coming from kind of an American company. So that's DeepSeek, and that's what's called a reasoning model. Now, when I go back to chat, let me go to chat here. Okay, so the models that you're going to see in the drop-down here, some of them, like O1, O3 Mini, O3 Mini High, etc., they are talking about uses advanced reasoning. Now, what this is referring to, uses advanced reasoning, is it's referring to the fact that it was trained by reinforcement learning with techniques very similar to those of DeepSeek R1, per public statements of OpenAI employees. So these are thinking models trained with RL, and these models like GPT-4o or GPT-4o Mini that you're getting in the free tier, you should think of them as mostly SFT models, supervised fine-tuning models. They don't actually do this like thinking as you see in the RL models. And even though there's a little bit of reinforcement learning involved with these models, and I'll go into that in a second, these are mostly SFT models. I think you should think about it that way. So in the same way as what we saw here, we can pick one of the thinking models, like say O3 Mini High, and these models, by the way, might not be available to you unless you pay a ChatGPT subscription of either $20 per month or $200 per month for some of the top models. So we can pick a thinking model and run. Now what's going to happen here is it's going to say reasoning, and it's going to start to do stuff like this. And what we're seeing here is not exactly the stuff we're seeing here. So even though under the hood, the model produces these kinds of chains of thought, OpenAI chooses to not show the exact chains of thought in the web interface. It shows little summaries of those chains of thought. And OpenAI kind of does this, I think, partly because they are worried about what's called a distillation risk. That is that someone could come in and actually try to imitate those reasoning traces and recover a lot of the reasoning performance by just imitating the reasoning chains of thought. And so they kind of hide them and they only show little summaries of them. So you're not getting exactly what you would get in DeepSeek as with respect to the reasoning itself. And then they write up the solution. So these are kind of like equivalent, even though we're not seeing the full under the hood details. Now, in terms of the performance, these models and DeepSeek models are currently roughly on par, I would say. It's kind of hard to tell because of the evaluations. But if you're paying $200 per month to OpenAI, some of these models, I believe, are currently, they basically still look better. But DeepSeek R1 for now is still a very solid choice for a thinking model that would be available to you either on this website or any other website because the model is open weights. You can just download it. So that's thinking models. So what is the summary so far? Well, we've talked about reinforcement learning and the fact that thinking emerges in the process of the optimization when we basically run RL on many math and kind of code problems that have verifiable solutions. So there's like an answer 3, etc. Now, these thinking models you can access in, for example, DeepSeek or any inference provider like Together.ai and choosing DeepSeek over there. These thinking models are also available in ChatGPT under any of the O1 or O3 models. But these GPT-4o models, etc., they're not thinking models. You should think of them as mostly SFT models. Now, if you have a prompt that requires advanced reasoning and so on, you should probably use some of the thinking models or at least try them out. But empirically, for a lot of my use, when you're asking a simpler question, there's like a knowledge-based question or something like that, this might be overkill. Like there's no need to think 30 seconds about some factual question. So for that, I will sometimes default to just GPT-4o. So empirically, about 80-90% of my use is just GPT-4o. And when I come across a very difficult problem, like in math and code, etc., I will reach for the thinking models, but then I have to wait a bit longer because they are thinking. So you can access these on ChatGPT, on DeepSeek. Also, I wanted to point out that aistudio.google.com, even though it looks really busy, really ugly because Google is just unable to do this kind of stuff well, is like, what is happening? But if you choose model and you choose here Gemini 2.0 Flash Thinking Experimental 0121, if you choose that one, that's also a kind of early experimental of a thinking model by Google. So we can go here and we can give it the same problem and click run. And this is also a thinking model that will also do something similar and comes out with the right answer here. So basically Gemini also offers a thinking model. Anthropic currently does not offer a thinking model. But basically this is kind of like the frontier development of these LLMs. I think RL is kind of like this new exciting stage, but getting the details right is difficult. And that's why all these models and thinking models are currently experimental as of 2025, very early 2025. But this is kind of like the frontier development of pushing the performance on these very difficult problems using reasoning that is emergent in these optimizations. One more connection that I wanted.
Şimdi reasoning modellerden bahsetti. Zaten artık o zaman da experimental'dı. Şimdi her yerde var. Mesela Claudio Code falan kullanıyorsanız, Opus'tu bilmem neydi. Orada thinking modunu çok görüyorsunuz. ChatGPT'de de aynı şekilde artık default oldu. Yani ekstra iç detaylarından bahsedecek olursak DeepSeek'in şu makalesi muhtemelen ilk fırsatta da bundan okuruz ne anlatmışlar burada ama bunu okumayı bu arkadaşın bir de Neural Network'ları anlattığı Zero to Hero bir serisi var. Muhtemelen bundan sonra da onu izliyor oluruz. Onu izledikten sonra biraz böyle low level detail'dan sonra şu white paper okunabilir belki DeepSeek'in. Daha önce yayınladığı white paper'lar da var. Onlara da bakılabilir. Thinking modda da sana cevabı verirken arka planda düşündüğü şeyleri gösteriyor. O zaman da en iyisini DeepSeek yapıyordu. OpenAI hala daha nedir? Biraz daha summary şeklinde veriyordu. Çünkü acaba farklı dataları millet görüp performans tahminde bulunma falan yapabilir mi diye o yüzden açmamışlar. Ama baktığın zaman da reasoning modellerinin popüler olması da DeepSeek ön planda. Çünkü adamlar yaptıkları şeyi white paper olarak yayınlamışlar. Ama benim gördüğüm şey gibi geliyor bana. Output tokenları daha fazla harcatsın diye yapılmış bir şey. Ee, Şeyde grafikte vardı. Reasoning modellerde output token daha fazla kullanılıyor ve daha fazla masraf demek aslında. Düşünerek cevap veriyor ya. O yüzden ChatGPT'de şey var. Cevap verirken thinking diyor ya, answer immediately diye bir buton var. Düşünmesini iptal edip direkt cevap ver kardeşim falan dedirtebiliyorsun ChatGPT'de. Onları anlattı. Yani şu zamanda bildiğimiz şeyler ama 11 ay önce dediği gibi experimental kaldı. Şimdi yenisine geçecek. Bakalım 45. dakikada ne anlatacak bize.
Wanted to bring up is that the discovery that reinforcement learning is an extremely powerful way of learning is not new to the field of AI. And one place where we've already seen this demonstrated is in the game of Go. And famously, DeepMind developed the system AlphaGo, and you can watch a movie about it, where the system is learning to play the game of Go against top human players. And when we go to the paper underlying AlphaGo, so in this paper, when we scroll down, we actually find a really interesting plot that I think is kind of familiar to us, and we're kind of like rediscovering in the more open domain of arbitrary problem solving instead of on the closed specific domain of the game of Go. But basically, what they saw, and we're going to see this in LLMs as well as this becomes more mature, is this is the ELO rating of playing game of Go, and this is Lee Sedol, an extremely strong human player. And here, what they are comparing is the strength of a model trained by supervised learning, and a model trained by reinforcement learning. So the supervised learning model is imitating human expert players. So if you just get a huge amount of games played by expert players in the game of Go and you try to imitate them, you are going to get better, but then you top out. And you never quite get better than some of the top players in the game of Go, like Lee Sedol. So you're never going to reach there because you're just imitating human players. You can't fundamentally go beyond a human player if you're just imitating human players. But in a process of reinforcement learning is significantly more powerful. In reinforcement learning for a game of Go, it means that the system is playing moves that empirically and statistically lead to winning the game. And so AlphaGo is a system where it kind of plays against itself, and it's using reinforcement learning to create rollouts. So it's the exact same diagram here, but there's no prompt. It's just because there's no prompt, it's just a fixed game of Go. But it's trying out lots of solutions, it's trying out lots of plays, and then the games that lead to a win instead of a specific answer are reinforced. They're made stronger. And so the system is learning basically the sequences of actions that empirically and statistically lead to winning the game. And reinforcement learning is not going to be constrained by human performance. And reinforcement learning can do significantly better and overcome even the top players like Lee Sedol. And so probably they could have run this longer and they just chose to crop it at some point because this costs money. But this is a very powerful demonstration of reinforcement learning. And we're only starting to kind of see hints of this diagram in large language models for reasoning problems. So we're not going to get too far by just imitating experts. We need to go beyond that, set up these like little game environments, and let the system discover reasoning traces or like ways of solving problems that are unique and that just basically work well. Now, on this aspect of uniqueness, notice that when you're doing reinforcement learning, nothing prevents you from veering off the distribution of how humans are playing the game. And so when we go back to this AlphaGo search here, one of the suggested modifications is called move 37. And move 37 in AlphaGo is referring to a specific point in time where AlphaGo basically played a move that no human expert would play. So the probability of this move to be played by a human player was evaluated to be about 1 in 10,000. So it's a very rare move, but in retrospect, it was a brilliant move. So AlphaGo, in the process of reinforcement learning, discovered kind of like a strategy of playing that was unknown to humans, but is in retrospect brilliant. I recommend this YouTube video, Lisa Dole versus AlphaGo Move 37 Reactions and Analysis. And this is kind of what it looked like when AlphaGo played this move.
Value.
That's a very surprising move.
I thought it was a mistake.
Wouldn't I see this move?
Anyway, so basically people are kind of freaking out because it's a move that a human would not play, that AlphaGo played, because in its training, this move seemed to be a good idea. It just happens not to be a kind of thing that humans would do. And so that is, again, the power of reinforcement learning. And in principle, we can actually see the equivalence of that if we continue scaling this paradigm in language models. And what that looks like is kind of unknown. So what does it mean to solve problems in such a way that even humans would not be able to get? How can you be better at reasoning or thinking than humans? How can you go beyond just a thinking human? Like maybe it means discovering analogies that humans would not be able to create. Or maybe it's like a new thinking strategy. It's kind of hard to think through. Maybe it's a wholly new language that actually is not even English. Maybe it discovers its own language that is a lot better at thinking. Because the model is unconstrained to even like stick with English. So maybe it picks a different language to think in, or it discovers its own language. So in principle, the behavior of the system is a lot less defined. It is open to do whatever works, and it is open to also slowly drift from the distribution of its training data, which is English. But all of that can only be done if we have a very large, diverse set of problems in which these strategies can be refined and perfected. And so that is a lot of the frontier LLM research that's going on right now, is trying to kind of create those kinds of prompt distributions that are large and diverse. These are all kind of like game environments in which the LLMs can practice their thinking. And it's kind of like writing, these practice problems. We have to create practice problems for all of domains of knowledge. And if we have practice problems and tons of them, the models will be able to reinforcement learn on them and kind of create these kinds of diagrams, but in the domain of open thinking instead of a closed domain like Game of Go. There's one more section within reinforcement learning that I wanted to cover, and that is that of learning in unverifiable domains. So far, all of the problems that we've looked at are in what's called verifiable domains. That is, any candidate solution we can score very easily against a concrete answer. So for example, answer is 3, and we can very easily score these solutions against the answer of 3. Either we require the models to like box in their answers, and then we just check for equality of whatever's in the box with the answer. Or you can also use kind of what's called an LLM judge. So the LLM judge looks at a solution and it gets the answer and just basically scores the solution for whether it's consistent with the answer or not. And LLMs empirically are good enough at the current capability that they can do this fairly reliably. So we can apply those kinds of techniques as well. In any case, we have a concrete answer and we're just checking solutions against it, and we can do this automatically with no kind of humans in the loop. The problem is that we can't apply this strategy in what's called unverifiable domains. So usually these are, for example, creative writing tasks like write a joke about pelicans or write a poem or summarize a paragraph or something like that. In these kinds of domains, it becomes harder to score our different solutions to this problem. So for example, writing a joke about pelicans, we can generate lots of different jokes, of course, that's fine. For example, we can go to ChatGPT and we can get it to generate a joke about pelicans. So much stuff in their beaks because they don't pelican in backpacks. What? Okay. we can try something else. Why don't pelicans ever pay for their drinks? Because they always bill it to someone else. Haha. Okay, so these models are obviously not very good at humor. Actually, I think it's pretty fascinating because I think humor is secretly very difficult, and the models don't have the capability, I think. Anyway, in any case, you could imagine creating lots of jokes. The problem that we are facing is how do we score them? Now, in principle, we could, of course, get a human to look at all these jokes just like I did right now. The problem with that is if you are doing reinforcement learning, you're going to be doing many thousands of updates. And for each update, you want to be looking at, say, thousands of prompts. And for each prompt, you want to be potentially looking at hundreds or thousands of different kinds of generations. And so there's just like way too many of these to look at. And so in principle, you could have a human inspect all of them and score them and decide that, okay, maybe this one is funny, and maybe this one is funny, and this one is funny. And we could train on them to get the model to become slightly better at jokes in the context of pelicans, at least. The problem is that it's just like way too much human time. This is an unscalable strategy. We need some kind of an automatic strategy for doing this. And one sort of solution to this was proposed in this paper that introduced what's called reinforcement learning from human feedback. And so this was a paper from OpenAI at the time, and many of these people are now co-founders in Anthropic. And this kind of proposed a approach for basically doing reinforcement learning in unverifiable domains. So let's take a look at how that works. So this is the cartoon diagram of the core ideas involved. So as I mentioned, the naive approach is if we just set infinity human time, we could just run RL in these domains just fine. So for example, we can run RL as usual if I have infinity humans. I just want to do, and these are just cartoon numbers, I want to do 1,000 updates, where each update will be on 1,000 prompts. And for each prompt, we're going to have 1,000 rollouts that we're scoring. So we can run RL with this kind of a setup. The problem is, in the process of doing this, I would need to ask a human to evaluate a joke a total of 1 billion times. And so that's a lot of people looking at really terrible jokes. So we don't want to do that. So instead, we want to take the RLHF approach. So in RLHF approach, we are kind of like the core trick is that of indirection. So we're going to involve humans just a little bit. And the way we cheat is that we basically train a whole separate neural network that we call a reward model. And this neural network will kind of like imitate human scores. So we're going to ask humans to score rollouts. We're going to then imitate human scores using a neural network. And this neural network will become a kind of simulator of human preferences. And now that we have a neural network simulator, we can do RL against it. So instead of asking a real human, we're asking a simulated human for their score of a joke, as an example. And so once we have a simulator, we're off to the races because we can query it as many times as we want to, and it's a whole automatic process, and we can now do reinforcement learning with respect to the simulator. And the simulator, as you might expect, is not going to be a perfect human, but if it's at least statistically similar to human judgment, then you might expect that this will do something. And in practice, indeed, it does. So once we have a simulator, we can do RL and everything works great. So let me show you a cartoon diagram a little bit of what this process looks like. Although the details are not super important, it's just the core idea of how this works. So here I have a cartoon diagram of a hypothetical example of what training the reward model would look like. So we have a prompt like write a joke about pelicans, and then here we have 5 separate rollouts. So these are all 5 different jokes, just like this one. Now, the first thing we're going to do is we are going to ask a human to order these jokes from the best to worst. So this is so here, this human thought that this joke is the best, the funniest. So number 1 joke. This is number 2 joke, number 3 joke, 4, and 5. So this is the worst joke. We're asking humans to order instead of give scores directly because it's a bit of an easier task. It's easier for a human to give an ordering than to give precise scores. Now, that is now the supervision for the model. So the human has ordered them, and that is kind of like their contribution to the training process. But now separately, what we're going to do is we're going to ask a reward model about its scoring of these jokes. Now, the reward model is a whole separate neural network, completely separate neural net. And it's also probably a transformer, but it's not a language model in the sense that it generates diverse language, etc. It's just a scoring model. So the reward model will take as an input the prompt, number 1, and number 2, a candidate joke. So those are the 2 inputs that go into the reward model. So here, for example, the reward model would be taking this prompt and this joke. Now the output of a reward model is a single number. And this number is thought of as a score, and it can range, for example, from 0 to 1. So 0 would be the worst score, and 1 would be the best score. So here are some examples of what a hypothetical reward model at some stage in the training process would give as scoring to these jokes. So 0.1 is a very low score, 0.8 is a really high score, and so on. And so now we compare the scores given by the reward model with the ordering given by the human. And there's a precise mathematical way to actually calculate this, basically set up a loss function and calculate a kind of like a correspondence here and update a model based on it. But I just want to give you the intuition, which is that, as an example here, for this second joke, the human thought that it was the funniest, and the model kind of agreed, right? 0.8 is a relatively high score. But this score should have been even higher, right? So after an update, we would expect that maybe the score should have been, will actually grow after an update of the network to be like, say, 0.81 or something. For this one here, they actually are in a massive disagreement because the human thought that this was number 2, but here the score is only 0.1. And so this score needs to be much higher. So after an update on top of this kind of a supervision, this might grow a lot more, like maybe it's 0.15 or something like that. And then here, the human thought that this one was the worst joke, but here the model actually gave it a fairly high number. So you might expect that after the update, this would come down to maybe 3.5 or something like that. So basically, we're doing what we did before. We're slightly nudging the predictions from the models using a neural network training process. And we're trying to make the reward model scores be consistent with human ordering. And so as we update the reward model on human data, it becomes better and better simulator of the scores and orders that humans provide, and then becomes kind of like the simulator of human preferences, which we can then do RL against. But critically, we're not asking humans 1 billion times to look at a joke. We're maybe looking at 1,000 prompts and 5 rollouts each, so maybe 5,000 jokes that humans have to look at in total. And they just give the ordering, and then we're training the model to be consistent with that ordering. And I'm skipping over the mathematical details, but I just want you to understand a high-level idea that this reward model is basically giving us the scores, and we have a way of training it to be consistent with human orderings. And that's how RLHF works. Okay, so that is the rough idea. We basically train simulators of humans and RL with respect to those simulators. Now I want to talk about first the upside of reinforcement learning from human feedback. The first thing is that this allows us to run reinforcement learning, which we know is an incredibly powerful kind of set of techniques, and it allows us to do it in arbitrary domains, and including the ones that are unverifiable. So things like summarization and poem writing, joke writing, or any other creative writing really, in domains outside of math and code, etc. Now, empirically, what we see when we actually apply RLHF is that this is a way to improve the performance of the model. And I have a top answer for why that might be, but I don't actually know that it is like super well established on like why this is. You can empirically observe that when you do RLHF correctly, the models you get are just like a little bit better. But as to why is I think like not as clear. So here's my best guess. My best guess is that this is possibly mostly due to the discriminator generator gap. What that means is that in many cases, it is significantly easier to discriminate than to generate for humans. So in particular, an example of this is when we do supervised fine-tuning, right, SFT, we're asking humans to generate the ideal assistant response. And in many cases here, as I've shown it, the ideal response is very simple to write, but in many cases it might not be. So for example, in summarization or poem writing or joke writing, like how are you as a human labeler supposed to give the ideal response in these cases? It requires creative human writing to do that. And so RLHF kind of sidesteps this because we get to ask people a significantly easier question as a data labelers. They're not asked to write poems directly. They're just given 5 poems from the model, and they're just asked to order them. And so that's just a much easier task for a human labeler to do. And so what I think this allows you to do basically is it kind of like allows a lot more higher accuracy data because we're not asking people to do the generation task, which can be extremely difficult. Like we're not asking them to do creative writing. We're just trying to get them to distinguish between creative writings and find the ones that are best. And that is the signal that humans are providing, just the ordering. And that is their input into the system. And then the system in RLHF just discovers the kinds of responses that would be graded well by humans. And so that step of indirection allows the models to become a bit better. So that is the upside of RLHF. It allows us to run RL. It empirically results in better models. And it allows people to contribute their supervision even without having to do extremely difficult tasks in the case of writing ideal responses.
Tamam. Tam bir saatte o zaman yorum da yapalım. Şimdi reinforcement learning'de demiştik yani olası şeyler var. Farklılarını deniyor, yolları var. Thinking modelinden bahsetmişti. Şimdi bunları yaparken aslında belli bir tanımlanmış domain var. Mesela matematikten bahsediyoruz, değil mi? Fiziksten falan bahsediyor olabilirsin. Bunlar verified domain diye geçiyor. Bir de unverified domainler var. Mesela bana espri üret, şaka üret gibi. Bunların bir verification'ı yapamazsın doğru düzgün, değil mi? Ha, var olanları yap desen, bana mesela temelle ilgili şaka yap desen onu belki anlayabilir. Değil mi? Verified yani daha önceden var resmi. Ama pelikanla ilgili şaka yap dediğinde nereden bilecek yani? Dolayısıyla bu tarz unverified domainleri de insanların yardımını isteyerek öğretiyorlar. Ona da Reinforcement Learning Human Feedback deniyor. Yani RLHF bir şeyi yaparken kullanıcıdan feedback bekliyor. Hani daha önceden vermiştim ya, iki tane cevap veriyor, hangisini beğendin ya da gibi. Senden mesela 5 tane şeyden sıralamanı istiyor. Ona göre veriyorsun ve senin verdiğin inputlara göre, feedbacklere göre kendini eğitiyor ve daha sonra sana soruyor. Burada da anlattığı buydu. Neyse, bir saati doldurduk arkadaşlar. Yarım saatlik bölümü bir sonraki yayında şey yaparız. Ben yavaştan kaçacağım. 4T, 4K, 1C abi senin yapmaya çalıştığını anladım ama teknolojik olarak anladım ama niye böyle bir şey yaptığını pek anlayamadım. Bunun için bildiğim kadarıyla OpenTelemetry kütüphaneleri var. LLM için OpenTelemetry kütüphaneleri. Ne yapıyor, ne ediyor onları raporluyor. İstersen bir sonraki yayında tekrardan konuşalım. Şimdi biraz geç oldu ama dinlediğiniz için teşekkür ediyorum. Gecenin bu saatinde. Bir sonraki bölümde de bunu kapatalım. Ondan sonraki bölümde bu Karpati'nin Zero to Hero Neural Network bölümü var. Yani Neural Network bir sonraki şey olarak, liste olarak koymamın sebebi de yani içinde biraz daha böyle hands-on, bu LLM'in train ettiği yerlerde hani hep neural net'ten bahsediyor ya, tokenları bir pipeline'dan geçirme, transformer logic. Neural network anlarsak eğer biraz daha hızlı ya da daha bir şeyleri anlayarak ilerleyebiliriz diye düşünüyorum. Tekrardan iyi geceler diliyorum hepinize. Daha sonra da tekrardan görüşürüz. Bay bay.